Welcome. I'm Steve Reynolds, President Professor in the School of Earth and Space Exploration at Arizona State University and author of 3 textbooks for McGraw-Hill. McGraw-Hill has nicely funded these virtual field trips for us, and we wanted to do another one, in this case of Monument Valley. This field trip will be a little different than the ones we've done because we got the video crew to Monument Valley, but then a blizzard hit and I physically couldn't get there. So we shot the video and photos and immersive 3D resources up there, but then we'll add me later. So a lot of this will actually be me off the screen. You'll just be seeing the videos and the photos and things like that. But we wanted to start with just telling you what we're going to do on this. Monument Valley is along the Arizona-Utah border and has some really nice characteristics that make it a wonderful place to teach students how to observe landscapes and how to think about them. For example, take a look at this scene behind me and think about the different components that make up this landscape. Landscapes are kind of complicated, and so you have to kind of say, oh, this landscape's composed of this and this and this and this, and this makes it more comprehensible. Take a look at this image behind me. It's one of the mittens for which Monument Valley is very famous. And for yourself, think about what components make up this landscape. And we'll let you do that for a bit, and then I'll talk about it. When you look at this landscape, it has just a small number of components. It has some layers that are best expressed down here in the pedestal below the mitten. And it also has some layers up in the mitten itself. There are some layers in the cliffy part, but you can't really see it. So there's layers, and there's a variation in the thickness of the layers. There's a very thick layer of sandstone up here and very thin layers down here. In addition to the layers, there are fractures. There are a whole series of fractures here, and the fractures are mostly vertical in this case. That's really common for fractures. These are kind of fracture, a joint where the rocks are just pulled apart just a little bit. But even these little ledges down here have fractures in them. So those are 2 of the main components. In addition, you can see that there's the difference between rocks that are still attached, that is their bedrock, versus rocks that are loose and laying around on the surface. And so those loose rocks, that's another component. And when we look at something like that as geologists, we don't focus on every single rock. We say, oh, look, there's a pile of loose material. We typically use the term talus for this. And we just think of that as one entity, but that's just another component. And then the thing that's really cool about this particular image, at the very base of it, there's sand that's being blown around by the wind. And so that's another component of loose materials, not bedrock. Other components that you can look at in here is the colors of the rocks. And in this case, there's some kind of reddish browns in here. Students often describe these rocks as red. Turns out that very few rocks are red. When you think of red, it's a fire engine. These are not fire engine red. And then these are a little bit more brownish because these have a stain on them. In this case, it's a stain that we call rock varnish or desert varnish. And a lot of it's wind-blown, iron oxides, manganese oxides, other stuff that has kind of coated the rocks. And the longer the rocks sit there, the darker they get. But so the color, and in this case some of the desert varnish, is another component. And another component are the shape of the rocks. In this case, this is described as a mitten because it looks like a mitten. And so that's yet another component. And the shape of the rocks is just due to the intricacies of erosion and weathering, and it's related to fractures and how the rock's fallen apart. But so when you look at a scene like this, you can break it into its individual components. And I have to tell you, on the very first day of class, I teach students how to look at landscapes, because I'm going to be showing them landscapes the whole semester when I'm teaching in person. And so I want them to kind of be able to look at this. And then as we go along, there are other aspects that are important. For example, in this case, the layers are basically horizontal, but in some areas, they're not horizontal. And so that's another thing to look at. And likewise, here the joints are vertical, but in some cases they're not. They're at an angle or they're horizontal, and so that's another component to think about. So take a look at this landscape and think about it from the standpoint of the components. Taking something complicated and trying to extract the main essence out of it is a process called disembedding. Cognitive scientists use it. I've used it a ton. And so really what we're looking at is this is a disembedding process to try to say, what's the signal in here from all the noise? We don't have to pay attention to every single one of these little joints in this lower sandstone ledge. But we just want to say, oh, look, it's got joints, and this is the orientation, and maybe you talk about spacing and other things like that. One of the other things that we as geologists do with landscapes that we've never really recognized or taught students is we do something that I've named trading location for time. And if you look at a scene like this, we look at individual elements. Like here's one of the mittens, the same one we just looked at. There's another mitten. And then over here on this side, there's a mesa. And what we do as geologists is we look at those, and in our brains, we see an evolutionary sequence, either going back in the past or going forward in the future. So what we're doing, we're taking individual objects, features in the landscape, and we're kind of seeing how they fit in an evolutionary sequence. So that's what I mean by trading location for time. We're not around long enough to watch all this evolve, but if we see what these different landscape features look like, we can kind of build an evolutionary sequence. In this case, you can imagine that the earliest sequence in here of what we see here is this mesa. That these mittens were once part of a mesa. And so in the past, there was a mesa in here, and then you started eroding and separating them and isolating these mesas from one another. And there are places where this upper sandstone is gone, and you just have a rounded hill. And that's starting to happen out in here. And so you have these kind of three phases in the landscape. You have the mesa evolving to buttes, and as the resistant sandstone erodes away, you make little rounded hills. And so there are these three components, and we commonly use a scene like this in the textbook to illustrate trading location for time. But it's something we do, and it's helpful for students to realize that you can either go forward or backward in time. For example, we can say, oh, here's what it used to look like in the past, but we can also look at a scene like this and say, what's it going to do in the future? And in the future, once the sandstone cap's gone, then that will evolve into just a little rounded hill. As this mesa gets eroded, at some point there will be more isolated buttes. So you can either go forward or backward when you're thinking of this strategy. I'm a structural geologist and field geologist, and one of the things that's really interesting about Monument Valley is the way that the joints, the fractures, control the scenery. In this case, you notice how this cliff looks fairly continuous. It's not broken up by a whole bunch of fractures, because you're now looking at a face that's parallel to the dominant orientation of the fracture sets. And so big pieces are falling off, but they're falling off along fractures that are trending parallel to the cliff. When we looked at the mittens, there were a whole bunch of fractures coming straight at us because we were looking perpendicular to this direction. So how a landscape looks really is highly influenced by the orientation of the fractures and the orientation of the face that you're looking at or the scene you're looking at compared to the orientation of the fracture. So let's turn our attention to the sequence of layers expressed in the buttes and the mesas of Monument Valley. So there are really 5 or so main geologic formations. The most dominant one is the cliff-forming sandstone. It's the Deshay sandstone. It's upper, lower Permian. And it's named for Canyon de Chelly in east central Arizona. Below that is a unit that's called the Organ Rock Shale. And it forms the pedestals. And you can see it's got a lot of fine-grained material, but it's got some little sand layers in it as well that are making the little ledges. Below the Organ Rock, but really not very visible, maybe a little bit back in some of these places back here, there's another cliff-forming sandstone that kind of forms the whole bottom of the valley, and it's called the Cedar Mesa sandstone. It's also early Permian. And that's kind of the bottom that you see. On top of the cliff-forming sandstone, on top of the de Chelly, you can see there's some ledges of a reddish-brown unit, and then there's an upper cliff. On top of these buttes, depending on where you are, there are two units. There is the early Triassic Moenkopi Formation, and then there's the late Triassic Chinle Formation. The basal formation of the Chinle is a really resistant basal conglomerate called the Shinnerup. And so some of these buttes get all the way up into the Shinnerup, and then the upper part of the Chinle is really easily eroded shales. It's the material that makes the Painted Desert and the Petrified Forest National Park, and it's got a lot of volcanic ash in it, so it's really easy to strip it off. So that unit's locally in the region present, but is not typically present in the buttes. The de Chelly, as you can see, it forms basically an unbroken cliff. And I always teach students, if you see a unit that forms an unbroken cliff and it's made of sandstone, it's nearly always a unit that was deposited by the wind. The reason for this is the wind is moving sand, but finer material gets blown out, coarser material gets left behind. So when you have sand dunes migrating across the countryside, you're just making sand. And so it's really hard to make discrete layers that stand out if all you're working with is sand. Now there would be layers in here if you got the right, you can see some hints of layers in here, and there would be cross beds in here, the curved beds that are associated with, in this case, wind. So those layers would be there, but they're not very obvious. So in general, when you see a big unbroken cliff, whether it's here or in Canyonlands or Zion National Park, those kind of rocks are usually deposited by the wind. The Organ Rock Shale, or Organ Rock Formation, depending on what your preference is regarded as an equivalent of the Hermit Shale in the Grand Canyon. And very few people doubt that correlation. And you can see it's got a lot of fine-grained silts and muds. And the Hermit Shale commonly is called the Hermit Formation because it's got a lot of silt and it's not all shale. So anyway, so that's the equivalent of that. The Cedar Mesa sandstone below is considered to be an equivalent of the Esplanade sandstone, the upper cliffy unit of the Supai group in Grand Canyon. So you essentially have a sequence that's Supai, Hermit, and then de Chelly is clearly a unit that's not expressed in the Grand Canyon. Some people think it might be Coconino, but I think there's a lot of evidence that it's a slightly older unit than the Coconino, and the Coconino overlies it in places over like by Canyon de Chelly. And so you're kind of looking at the same interval of red rocks that you see in the Grand Canyon, but slight differences in what units are present, because things like big sand seas that deposit something like the de Chelly, they don't go on forever. And so the de Chelly sand sea did not make it to the Grand Canyon, did not make it to central Arizona. It was pretty much restricted in this particular part of the region near the Four Corners. So how about the top two units? The Moenkopi is considered to be pretty much a near sea level tidal flat, especially as you go further west, and then low-level kind of fluvial rocks. There's sandy units and silty units, so floodplain and channel deposits, fluvial. And again, that's an early Triassic rock. And then the Shinnerup it's a conglomerate. It's very clearly a fluvial rock and terrestrial. And at that time, the Cordilleran Arc was really putting out a lot of volcanic ash. And so the rocks above the Shinnerup and the rest of the Chinle, they're loaded with volcanic ash, people have done a lot of work on those rocks. They get zircons that are like 220 million years out of it. And so you're going from a relatively quiet tectonic period in here, represented by the Permian rocks and by the late Triassic rocks. And then by the time you go into the Chinle Formation, you're starting to see expressions of all the tectonic activity associated with subduction along the west coast of North America. Although they're not in this scene, on top of the Chinle, there are a whole sequence of rocks called the Glen Canyon Group, and that includes the Navajo Sandstone and the Cayenta and some of those other really well-known formations of the Colorado Plateau. They were here, and they were eroded away, and they're gone. Likewise, this sandstone, the Deshay, is a remnant of an extensive layer that once covered the whole area, was compacted and made into a hard rock, and then has now been eroded into the various landscape features you see. A really interesting aspect of the landscapes of Monument Valley is the fact that you have these modern sand dunes nestled in and among the sandstone cliffs of the Deshay Sandstone. The sand in these is being derived from erosion and weathering of the old sand dunes, of the Permian sandstones. And so that material is being weathered off, and then the wind is moving it. And so we have some nice videos showing the wind actually blowing in here. When we were trying to do videos up here, the wind was blowing 40, 50 miles an hour, so you got a really good chance to look at a lot of wind action. And so it's really interesting to think that these sand grains came from that sandstone, but the grains in that sandstone, they had to come from some other place where you're weathering presumably granites and things like that. Most sand comes from weathering of granites. And so, this sand has kind of been through a bunch of phases. So in this place, you have modern sand dunes where the sand is derived from Permian sand dunes, as represented by the Deshay Sandstone. But the sand grains in the Deshay Sandstone had to come from someplace else. This is a case where we've done detrital zircon work in here, where you grind up sandstones and you can probe with a laser individual zircon grains and get the dates of individual zircons. When you do that in here, as people had done for other sandstones around, is what we find is there are a lot of zircons here that are about 1 billion years old. It's an odd age for the Southwest. The ancestral Rockies, we know what age the rocks are in the ancestral Rockies, the local mountain ranges in Pennsylvania and Permian time. And those are 1.7 and 1.4 dominantly. And yet we have all these 1 billion-year-old zircons. And the explanation is that these zircons had to come from some place that has 1 billion-year-old zircons. And so you start looking around, you say, what part of North America has 1 billion-year-old zircons? And it turns out it's the Appalachian Mountains. There's a province in eastern North America called the Grenville Province. It's about 1 billion years old. And it's loaded with zircons. It has a bunch of zircons compared to any other volume of rock you might look at. And so the results of our studies in here with the tidal zircons is that a large percentage of the grains came from the Appalachian Mountains. Some came from the ancestral Rockies, like we taught students for years. But this was a place where you had a consensus and you just blew it apart because you had a new method. And so in here, when you look at these, you realize a lot of this stuff came from the Appalachians. So you had to have river systems in eastern North America, in the Appalachians. That was the big continental divide at the time. You had Africa off to the other side and western North America on this side. The rivers were eroding from the Appalachians. They were having to transport the grains all the way across the continent. And then once they got kind of close to where we are, then they got moved around by wind, they got moved around by longshore currents, they got moved around by local river systems. But you had to bring those zircons all the way across the continent and then rework them, and then they ended up being as individual grains in the Deshay Sandstone. And we didn't analyze these, but I can tell you that these modern sand dunes would have a lot of Appalachian zircon grains in them. So it's just a really interesting story, both for how we've used a new method to kind of, throw off a consensus that we had that this is how things form. And also just thinking about the prolonged history of some of these grains and the history's recorded in them. And you could come up here and scoop these grains and analyze them, separate the zircons and analyze them, and you could say, those are grains that don't have any business being here in southwestern North America, but they're very similar to what's in the Appalachians. On behalf of Julia Johnson and myself, authors of the Exploring series of textbooks, and on McGraw-Hill, we thank you for participating in this and joining us. And we hope that you've found some things that you can share with your students. Thank you very much.